Finally, this lecture that I'm not exactly sure how, but somehow I have two children and both have grown up to be hypochondriacs. Not sure what or how it happened, but they both like to get on WebMD and figure out how they can turn some little ache or pain into cancer. So this morning, just after I got done teaching at the podiatry school, we get a phone call. It's my son, and he's all upset. He's at work, and he's all upset because he's decided that he has cirrhosis, or he's concerned that he might have cirrhosis. So I asked him. It looked it on WebMD. I hate that word. It's embarrassing. So I said, well, why do you think you have cirrhosis? He said, my poop isn't as dark as I think it should be. So my son is spending way too much time staring at his poop, deciding it's not as dark as it should be, and from WebMD has decided it's probably because of liver malfunction. I said, I would have suspected the gallbladder first and told him why, because I don't want him to get too comforted by it. I said, but he said, so you don't think it's cirrhosis? I said, no. I know about the liver. As a matter of fact, I'm going to give a 2-hour lecture about the liver this afternoon. Don't worry, it's not going to be 2 hours. But the liver does everything then. If you're worried that your poop's not dark enough, think about the gallbladder first. So there's my excitement for today. Sadly, that is my excitement for today. So we're going to talk about the liver. Now you already know how to summarize everything we're going to talk about with this in one brief sentence. That's basically, if you don't know anything and somebody asks, where does this happen to your body, say liver, because it gives you the best chance of being right. So all we're trying to do, I've said that to you a number of times over the last semester plus. All we're going to try and do today is give you some idea, just kind of summarize some of the things we already talked about, some of the things we haven't talked about that you may already know. So this is what we're going to talk about today. And it's pretty amazing what the liver does. Functions, I've got 10 functions written down on this slide. Maintain homeostasis of nutrients. What do I mean there? In terms of it helps to maintain carbohydrate homeostasis because the liver is the seat of gluconeogenesis. And of all the glycogen in your body, liver has the highest concentration of glycogen. And when it breaks glycogen down, unlike muscle that has the most glycogen, liver shares the resulting glucose with the rest of the body. So that's gluconeogenesis and glycogenolysis are the two reasons, say, that the liver is involved in carbohydrate homeostasis. In terms of lipid homeostasis, you know from last week, or you might vaguely remember from last week, that the liver is involved because the liver is making VLDLs and HDLs. And it's the repository of cholesterol. The liver during the bad times is going to pick up fatty acids from the blood and convert them to ketones. So ketogenesis primarily taking place in the liver. And then the liver also can participate in amino acid homeostasis and metabolism of amino acids, not just for gluconeogenesis. Liver function number 2 is a storehouse. It's a place to store nutrients. And primarily here, I'm thinking of glycogen, but also the liver, because of its capacity for making fatty acids, also can form triglycerides and not just ship them out as VLDLs, but in times of prolonged, really good times, the liver can start to store triglycerides and develop a fatty liver. Also, in lipids here, the liver ends up kind of storing it, has trouble getting rid of cholesterol, another type of lipid. Function number 3, the vast majority of plasma proteins are synthesized by the liver. These important, particularly important ones would be most of our clotting factors are made by the liver, and also albumin, a good non-specific transport molecule and most abundant of the plasma proteins. Number 4, liver, we saw a couple of lectures ago from me, synthesizes and releases bile. It synthesizes bile, it synthesizes and releases it primarily in response to what signal? Huh?
Secretin.
Secretin, right? Secretin stimulates the liver to make more bile. It releases it to be taken up and stored by the gallbladder. Okay, number 5, it processes and excretes bilirubin. And bilirubin was what?
Byproduct of RBC breakdown.
It's a product, a waste product of heme catabolism. Okay, 6, detoxification and excretion of drugs, hormones, and toxins. The cytochrome P450 system that's in the liver is one of 2 important ways that work at doing that. We're going to talk about those for a little bit. 7, it's where we, if we can, with the fat-soluble vitamins, we have the ability to store or accumulate those, especially vitamins A and D, and liver is involved in the processing of vitamin D into its active form, calcitriol. Also, vitamin B12 can end up getting stored in the liver. Iron storage, that would be iron bound to apoferritin, that can occur in the liver. So we can have a reservoir of iron. Don't want it to become too abundant though. Number 9, synthesis and release of somatoledins, are also called insulin-like growth factors. That occurs in the liver in response to the presence of growth hormone. And then cleansing of blood, of bacteria in the blood. So that's a lot of really varied functions the liver participates in. So a couple of notes about each of them. When you think about maintaining homeostasis of nutrients, we have a number of different hormones that are going to help to regulate and control it. From human growth hormone, testosterone and estrogen can do things, thyroid hormone, drawing a blank on another one I was going to say, epinephrine, and linked to that, cortisol. So there's lots of things that have impacts on blood glucose and lipid levels in the blood. But the liver is going to be one of the key players in how we're going to help regulate it. So signals to the liver to tell it to do one thing or another. And it's the first place I look. It's our first line of defense against the drop in blood glucose. And the reason it's a first line of defense, and we were going to look at that, we already know, we said on the previous slide, there's glycogenolysis and gluconeogenesis. If you start to see a drop in blood glucose, what's the first thing that the liver is going to start doing?
Gluconeogenesis?
No.
Glycogenolysis.
Good guess, yeah. Just pause momentarily. You get it. Glycogenolysis. Why would it do glycogenolysis faster than before gluconeogenesis?
To use your storage of glucose.
It's right there, and we start breaking it down. If we're going to start, by the way, I'm going to start because this time a year from now, you're going to be done with national boards, right? Part 1. Successful. If we're talking about glycogenolysis, what's the enzyme that does most of the breakdown of glycogen? What, we haven't started studying the boards already? What's the primary enzyme for breaking down glycogen? Glycogen phosphorylase, and then it's fair game for them to leave off the glycogen, just say phosphorylase, and it's A. So it's one of those enzymes that's a superstar and only has to go by one name. Okay, so glycogen phosphorylase starts to break down glycogen. And what's the initial product of glycogen breakdown? By glycogen phosphorylase A? Glucose 1-phosphate. And glucose 1-phosphate becomes glucose 6-phosphate. And glucose 6-phosphate can become glucose. And what enzyme is present in the liver but not in skeletal muscle allows us to untrap the glucose by converting it from glucose 6-phosphate to glucose. This is like watching Jeopardy, isn't it? Glucose 6-phosphatase, right? It clips off the phosphate. So liver has glucose 6-phosphatase. Skeletal muscle, brain, neurons, they don't have it. It untraps glucose. One other thing allows glycogenolysis in the liver to help maintain blood glucose. Not just the presence of glucose 6-phosphatase, but what other thing? What other characteristic of the liver allows it to export glucose during those bad times?
Gluten transport?
The type of gluten transporter it has. What kind of glucose transporter does the liver have? I've forgotten the number, but what's the characteristic of the glucose transporter? During the bad times. It's an insulin-independent glucose transporter. So glucose transport is still on the membrane, you can export it. Okay, so glycogen phosphorylase, really easy to turn on. It's a cyclic AMP-dependent cascade. That's why glycogenolysis takes place quickly. But we have, even though the highest concentration in the body, a finite amount of glycogen, so we can fly through that pretty quickly. Gluconeogenesis is the liver's next line in the first line of defense. And gluconeogenesis, what are we doing with gluconeogenesis? We're making glucose from other carbon sources. Now, what would be a good carbon source to think of here? Because this is the bad times.
Fatty acids.
Not fatty acids. That's a good note to make right now. Fatty acids, any even numbered fatty acid does you no good for gluconeogenesis. An odd chain length fatty acid gives you 1/2 of a glucose per fatty acid. So basically, lipid catabolism doesn't do us any good for gluconeogenesis. Where are we going to get carbons if we're not getting them from lipid breakdown, triglyceride breakdown?
You do amino acids or
Amino acids. Where are you going to get your hands on amino acids during the bad times?
Catabolism.
muscle.
Muscle. I know this doesn't help much. But Tim, you said fat doesn't help. Okay, from breakdown of skeletal muscle. So during the bad times, skeletal muscle starts to break down. And when it starts to break down, we dump amino acids into the blood. But 2 amino acids in particular are elevated in the blood during the bad times. Alanine and, begins with the G, glutamine. And the alanine's headed where? To the liver. And what's the liver? What's the first thing the liver's going to do with the alanine? It deaminates it, but by what process does it remove the amine group? There's deamination and there's transamination. And when you remove the amine group from alanine, what does the liver end up with? Pyruvate, which is where in most biochemistry books they start the story of gluconeogenesis. It's half a glucose, and we run glycolysis in reverse. Okay, except for bypassing three key regulatory enzymes. What are the three key regulatory enzymes of glycolysis? Axokinase is the first one, bypassed by glucose 6-phosphatase. What's the next one? Phosphofructokinase, which is bypassed by what? Fructose 1,6 bisphosphatase. We remove a phosphate, one of the phosphates from fructose 1,6 bisphosphate. And the third and final key regulatory enzyme of glycolysis? Pyruvate kinase, and that's the one that has a couple of enzymes involved in bypassing it. Anybody remember one of them? Pyruvate carboxylase would be kicking it out, and then there's the PP carboxykinase, PCK. Okay, so all that's going on in the liver. By the way, that amine group that we got rid of with transamination, what does it become? Urea. So the liver makes urea. And what's the enzyme that makes urea? Arginase. Arginase is the enzyme that makes urea. And if they ask you that question on national boards, I will guarantee you they'll have uricase and urease there. Okay, so they're there to be distractors. Okay, so we can regulate blood glucose, and we just reviewed for national board simultaneously. We take fatty acid carbons and convert them into triglycerides. If times are good, the liver gets fatty acids from the diet. Okay, they were being distributed in what form, what structure? Dietary triglycerides are transported in blood in what form? Chylomicrons, and as we break them down using what enzyme? Lipoprotein lipase, we start seeing fatty acids. When fatty acids find themselves cut apart from a triglyceride and they're floating around in plasma and it's aqueous, and I'm scared and I don't like it here, I can't swim, what are they going to do? Attach to albumin or get the heck out of the blood as quickly as possible. So those fatty acids attached to albumin, where can they end up? There's one place they might eventually end up. The liver. What's the liver going to do with the fatty acid during the good times?
Storage.
It can take it and it can repackage it as a triglyceride. What's it going to do with that triglyceride? Could store it, we could accumulate it in fat globules inside the liver cell, the hepatocyte. Or what? Yeah, let's package it up as a VLDL and dump it out and send it once again out to the rest of the body. Meanwhile, during the good times, liver's getting a lot of glucose, and it can be taking it through glycolysis to acetyl-CoA, and from there into fatty acid synthesis to make brand new triglycerides. Package it up in VLDLs and send it on its way. Now, during the bad times, what's the liver going to, what's happening? During the bad times, hepatocytes, and this is all theoretical to me, obviously, hepatocytes are being told, break down those triglycerides that you've been so diligently storing all these years. And so the triglycerides, anybody remember the enzyme in triglycerides? It starts to break down triglycerides inside the adipocyte. Begins with an H. Called hormone sensitive lipase, or HSL. And so hormones signal, hey, it's the bad times. Like, and activate the HSL. So things like low insulin or elevated glucagon or the presence of epinephrine, those are hormones signaling, telling the hormone-sensitive lipase become active. Elevated insulin inhibits hormone-sensitive lipase. It's a signal saying, no, times are good, store for the future. So HSL starts to break down triglyceride. And the fatty acids are dumped into the blood. And this is during the bad time, so what's going to happen to them? You're a fatty acid. You've just been thrown out of the, you were part of a triglyceride in a whole big city of triglycerides. You've been clipped off and thrown out into the blood. How do you feel about it?
Not bad.
Unhappy. What are you going to do?
Fine.
Bind to albumin. Where are you going to go? Liver. What's the liver going to do to the fatty acids in the bad times?
Ketones?
It's going to convert them to ketones. It'll take them through beta oxidation, get acetyl-CoA, and start to rebuild. As it rebuilds, taking two acetyl-CoAs, combine them, and get acetoacetyl-CoA. Add a third one on, so now I've got a 6-carbon fragment, and that's hydroxymethylglutarol-CoA, or HMG-CoA. That's a good one to remember. Just remember HMG-CoA. You may, if you see it spelled out, you say, hey, look, there's an H, an M, and a G. HMG-CoA is the immediate precursor of the first of the ketones. So it's got 6 carbons. We're going to cut 4 of them off. And what we have is 2 acetates bound to each other. So it's called acetoacetate. And that's the first of the 3 ketones. Now the liver can then, again, this is what the liver is doing during the bad times. Liver can take that acetoacetate and reduce it, add a couple more electrons, make it worth 3 more ATPs. And so it converts a lot of what it first produces, acetoacetate, is produced to the primary ketone exiting the liver, and that's called 3-hydroxybutyrate, also called beta-hydroxybutyrate. Same thing. Number 3 carbon is the beta carbon. Okay, so what's the liver producing in terms of lipid homeostasis during the bad times? Ketones, specifically beta-hydroxybutyrate and acetoacetate. And then as those circulate, why did it do it? Because these are water soluble. Fatty acids, not so much. As some of the acetoacetate is circulating, it spontaneously loses its carboxyl group. And becomes, instead of acetoacetate, it becomes acetone. The acetone is highly volatile. We can't metabolize it. It's highly volatile, so it comes off in a person's breath. That's that fruity smell that untreated diabetics can have in their breath because they have the ketoacidosis. Okay, all that from one slide. Don't worry, they're not all going to be like that. Okay, liver can store glucose in the form of glycogen. We talked about some of that. Now, another thing we mentioned, or maybe I've mentioned it before, I don't know if we've gone into it, that of all the carbohydrates you eat, I think this was in FLS, all the carbohydrates you eat, if you look at the simple sugars in those carbohydrates or making up those carbohydrates, 80% is glucose. The remaining 20%, about 10% is galactose and 10% is, I just drew a blank. Oh, fructose, thank you. Okay, so the glucose can be taken up by lots of cells, most cells in the body, especially during the good times. The galactose and fructose, there are pathways that they are energetically, they have the same net yield as a glucose molecule. You just need a couple of different enzymes to get them into the glycolytic pathway. those enzymes we primarily find in the liver. So that 20% of the dietary sugars, the 20% that aren't glucose, are primarily used by the liver also, and can be used for glycolysis or gluconeogenesis. Okay, we talked about glycogenolysis and gluconeogenesis already. And remember, with glycogen, the highest concentration in the body is in the liver. The greatest amount of glycogen in the body is in skeletal muscle. Lipids, we just talked about the end of last week, or my most recent lectures from last week. The liver makes VLDLs and HDLs and produces ketones that we just talked about. In addition, the liver is the receiving, the central repository of chylomicron remnants and LDLs, and it's also where HDLs come back to disappear. Okay, the VLDL, so we're doing this in a different sequence now. VLDLs, how would you know a VLDL from these other structures? What's the characteristics of VLDL? There's apoprotein B100, what else? How do you tell the difference between a VLDL and an LDL?
A lot of cholesterol.
Okay. If triglycerides greater than cholesterol, there's apoprotein B100, it's a VLDL. If cholesterol is greater than triglyceride and you have apoprotein B100, it's an LDL. Okay, so the purpose of VLDLs is to do what?
Transport triglyceride.
From
The liver.
the liver. As how would you distinguish it from a chylomicron? Chylomicron, we'd see apoprotein B48, but what about the triglyceride?
It's from the digestive.
That's from the diet, whereas a VLDL contains liver-derived triglycerides. So one has just come into our body, the other one was made inside of our body. Okay? And so it's sending it out for distribution. HDL, quick thing for HDL, what do you associate with HDL now? Has cholesterol, what about it? It was born with cholesterol.
There's a lot of it.
Yeah, it comes back to the liver eventually with even more cholesterol than it was born with. So it does that because it's scavenging cholesterol. And if you looked at the crust on the HDL, what would you see? What would you expect to see? ApoE and C2. Okay? That's its other function, is to temporarily donate those to the chylomicron and the nascent chylomicron and the nascent VLDL to activate them. Okay, good. Ketones, let's talk about them. Well, one other thing about ketones, where are they made? Liver, that's why we're talking about them here. And the immediate precursor of acetoacetate is what? HMG-CoA, hydroxymethylglucuryl-CoA. HMG-CoA is not only the immediate precursor of the ketones, but it's also an intermediate in another pathway that takes place in the liver, involving lipids. HMG-CoA is also, this is where the fork in the road occurs. We either go down one route to become ketones, or we go down the other route to become cholesterol. So cholesterol synthesis takes place in our body, and specifically in the liver. Okay, so with amino acids, a couple of important components for the liver. Liver primarily uses amino acids from protein breakdown during the bad times for gluconeogenesis. So it's amino acids, important source of carbon for gluconeogenesis. And then number two, Hepatocytes are the place where we primarily synthesize other amino acids. So what other amino acids? This is our opportunity to remember that not all amino acids can be made in our body. Some we absolutely have to get in our diet, either because we can't make them or we can't make enough of them. The ones that we need to get in our diet are the essential amino acids, and that's Private Tim Hall. So what kind of amino acids can the liver make? Everything other than Private Tim Hall. So memorize Private Tim Hall. Pretty much most every released national board exam that I've seen has had a question about essential amino acids. Me not being able to memorize well, all I did was memorize PBTTIMHALL. I was spotting myself Tim because I figured I shouldn't be forgetting that one. And then over time, I'm pretty sure that the V is for valine. P, probably phenylalanine. But where I accidentally memorized things was Hall. So does anybody know the essential amino acids that are indicated by HALL? Histidine, not alanine, arginine, and lysine. Histidine, arginine, and lysine. I've heard those together before. What are they? Those are the basic amino acids. Well, what's the other L for? Leucine. Lysine and leucine, I've heard those before. Those are purely ketogenic amino acids. That means we can metabolize leucine and lysine, but we can't use them for gluconeogenesis. We can make ketones from them. So those I memorized purely accidentally. But this happened, so I'm proud of myself. Okay, and here we have, this is the liver is the spot where we're going to make urea. The terms of storing nutrients, we touched on those now. Glycogen, the highest concentration of it. Oh, another thing, why is the liver getting such a high concentration of glycogen? And I'd say there are two reasons why the liver, we should expect the liver to have a lot of glycogen. What would those two reasons be? Okay, it comes straight from, the liver gets first shot at any dietary glucose we cook in because of the hepatic portal system. Okay, that gave it first dibs on this, but it doesn't mean that it had to take advantage of that. What allows it to take advantage of that?
Glucokinase.
Presence of glucokinase. Now, glucokinase is a close relative of hexokinase. Okay, glucokinase, let's see, how should I phrase this? Glucokinase has a high Vmax and a high Km. What does that mean? What's the importance of that? Glucokinase compared to hexokinase has a high Vmax and a high Km.
Which is this big
What's the consequence of having a high Vmax?
Action goes faster.
I can work really fast. You give me glucose, I can trap it really fast. I can convert it to glucose 6-phosphate. What's the impact of a high Km? What does that mean?
It takes a lot to
Yeah,
saturate.
I've got a low affinity for glucose. I can convert it quickly, but I got a low affinity. So the only time I'm really going to be active is right after you eat. During the good times, I am built to trap. Okay? that's a great opportunity for them in national boards to be able to kind of combine two concepts. And that would be glycogen metabolism and enzymology. Okay, lipids, they can be stored in the liver also, just not, it's more associated, say, with a disease state or pathological state. You don't want your liver becoming fatty, but if you want to raise geese for foie gras, then you start packing corn down through funnels into their gullet, and it's illegal in most countries now. Another thing to do with lipids, not only can the liver make triglycerides and store them, but also it tends to accumulate cholesterol, and cholesterol is used in bile salt synthesis, as we saw last week, which is important for emulsifying dietary lipids, so we can break them up efficiently and get them into the body. Okay, synthesize and release plasma proteins. Just if you can think of, or in a test question, especially a board question, if you see a list of plasma proteins, just kind of by default start thinking probably made in the liver. Big exception are going to be the gamma globulins, the antibodies. But most everything else is going to be made by the liver. Clotting factors is importance here. We've got you'll talk about clotting factors next fall in renal and blood. But there's comfortably over 50 clotting factors, some procoagulants, others anticoagulants, that at any moment in time are determining whether you're going to start clotting your blood or not. Okay? So it's really important. We've got everything there in your blood ready to react, ready to go, to keep your blood from running out of your blood vessels. But we have to keep that in check and only use it when it needs to happen. So it's this balance of pro and anticoagulants, but we're living kind of life on the edge, that we've got this and we don't want to coagulate all of our blood. But some important clotting factors made by the liver would be things like fibrinogen, which is the inactive precursor of fibrin, which makes a mesh that traps the clot together, holds the clot together. Prothrombin, which is also called factor 2, Roman numeral 2. And this is something that is inactive, produced by the liver, and it gets converted to thrombin, and that triggers clot formation. Factor 7, a variety of other factors that got Roman numerals, most of them come from the liver. Now, an important thing to deal with clotting factors, and also ties into the liver, is the liver needs vitamin K in order to make potentially active clotting factors. So when the liver is synthesizing these clotting factors in their inactive state, it's during the synthesis that vitamin K is necessary. Okay? 4 clotting factors need vitamin K, 2, 7, 9, and 10. Okay? And if vitamin K is low, if you have a deficiency in vitamin K, the liver will still make factors 2, 7, 9, and 10. Everything will look like we're ready to go, but when it turns time to activate them, to use them, they don't work. It's sort of like, at least in the movies or television I've seen, where the good guy gives the bad guy a pistol, but they've shaved down the firing pin. So it looks like a gun, it's a loaded gun, but when they go to pull the trigger, it doesn't fire. Okay? Same thing here. If you're missing vitamin K during synthesis, the liver makes what looks to be 2, 7, 9, and 10 ready to rumble, but when we try to activate them, they don't work. And the other thing that can happen is you don't have a deficiency of vitamin K, but instead, we've given you a vitamin K analog. That vitamin K analog gets into the liver and interferes with vitamin K being able to be present during the synthesis. So when you give this vitamin K analog, you produce non-functioning factors 2, 7, 9, and 10. So you interfere with blood clotting. And that analog is called Coumadin when it's sold to people. It's called a blood thinner. But when it's sold in rat poison, it's called warfarin. And warfarin comes from Wisconsin Alumni Research Foundation, WARF, where they discovered it. Had something to do, it occurred in feed that they were feeding to cattle, and the cattle were starting to develop clotting problems. So vitamin K is important for the liver to have access to in synthesizing clotting factors. Albumin, the most abundant of the plasma proteins, probably 10 times more concentrated than any of the other plasma proteins except for the gamma globulins if you've been sick recently. Albumin's important for a couple of reasons. One, it's a good non-specific binding agent, so it helps to transport things in the blood, either fatty acids or drugs. And when you're prescribing drugs, it becomes important for you to know how, if you prescribe a new drug, it may displace some other drug that the patient is taking, and suddenly they may develop a toxic level of that drug, whereas it had been okay previously. So albumin is good to be able to help transport things. The other important function for albumin, being the most abundant of the plasma proteins, and it's too large, plasma proteins don't get through capillary pores, so we have a lot more protein, soluble protein in plasma than we do in the interstitial fluid. That means that albumin, along with the other plasma proteins, is sucking water into plasma from the interstitial fluid. And that's important because at the same time as blood is flowing through a capillary, the hydrostatic pressure, the blood pressure inside the capillary, is pushing water out. So albumin helps to balance between the pushing of the water out and the sucking of the water back in. Consequently, if you have liver disease, and the liver can no longer make enough albumin, one of the potential problems is you're not going to be sucking water back into the blood as strongly as hydrostatic pressure is pushing it out. So you start to develop what? What do you call, in general, the loss of water from the plasma into the interstitial fluid? That would be edema. Now, when it's happening globally, there's a specific type called ascites, A-S-C-I-T-E-S. And so the fluid can start to accumulate in the abdominal cavity. You can see people with liver disease that start to appear wasted, but then they have a distended abdomen. You can see that in the U.S. It would probably be more likely to be as a result of alcohol abuse or liver disease in one form or another. In third world countries, it's probably because of starvation and the wasting of bone and the metabolism of proteins to form what? What would happen? Why do you see those pictures of the little starving children?
Oh, kosher.
Yeah, but why do they have a distended abdomen?
It's not the proper proteins to hold their cells together. They leak out intracellular fluid into the abdominal space.
Right, but that's called ascites, and why does the ascites develop? Because they have fewer plasma proteins. What's happening to the plasma proteins there? Huh?
What it needs for energy.
specifically gluconeogenesis. Wasting of muscle protein and even wasting of the protein in the plasma protein. Doing good. Okay, we synthesize and release bile. Okay. Bile contains bile salts for emulsification. How would you recognize if they asked you about bile salts? How would you know they were talking about bile salts?
Chocolate.
Words look like chocolate, right? So colate. If you have taurocolate or glycocolate from taurine or glycine, that's a bile salt. If you have cholic acid or just cholate, that would be a bile acid, or chenodeoxycholate is another bile acid. So they help to form micelles. What's a micelle?
It's the packaging of triglycerides.
Packaging of triglyceride,
Cholesterol ester.
cholesterol esters, and
Phospholipids.
phospholipids along with the bile
That's a bile
salts.
salt.
Where would you find these micelles?
Mucosal cells.
Outside the body.
In the lumen of the intestine, outside of the body. Okay. Bile also contains the bilirubin and the cholesterol. That's produced by the liver. It's concentrated and stored in the gallbladder. The gallbladder releases the bile in response to what primarily? Cholecystokinin or CCK. And what's the best stimulus for cholecystokinin? Lipids where? In the duodenum. So dietary lipids in the duodenum. What might happen if you eat a low-fat diet for a long enough? Again, theoretical. Huh?
Because of the salt.
Gallstones, yeah. So if we don't get the signal to release the bile, or if the bile duct is kind of blocked off for one reason or another, then the gallbladder keeps concentrating the bile, pumping out salt, or pumping salt back into the body and the water following. As we start to concentrate the bile salts and the cholesterol, we can get precipitation, forming gallstones. And then when they start to try and go down and pass through the canal, it can be painful. People can feel really sick from it. And so what could you do about that? You could remove the gallbladder. You could try ultrasound to break up some stones, but you could remove the gallbladder. Well, what's going to happen to a person if you remove their gallbladder? Decent, you could get there, but you'd have to do something. Can a person survive without a gallbladder? Yeah, it's not like a heart, right? Oh my God, my gallbladder is gone. Okay, so what would they have to do? Let's reduce our fat intake. Okay? Will I ever be able to digest fats again? Sure. Just can't handle large amounts as well as I used to. The liver is still producing. When I eat something and it gets into my duodenum, I still release secretin. The liver starts to produce more bile. The bile will just flow. There's no place to accumulate in the gallbladder, so it'll flow right down and help to emulsify, just not produce as much. You can't get that big surge of bile salt. So if I eat a lot of fat and get just a little bile salt, then I'm not going to digest much of the fat, and we're going to have something like fat foe situation or ally that we talked about last week, and so end up with this steatorrhea. And my son would be calling me. Bilirubin, waste products of heme catabolism. How did the bilirubin get to the liver? largely transported by albumin. And then in the liver, it conjugates the bilirubin. So the bilirubin binding to albumin to get the liver suggests what? If you hear compound X binds to albumin to get to the liver, what does it suggest?
Hydrocodone.
Yeah, the compound X doesn't like water much. Otherwise, what did it need albumin for? So then when it gets to the liver, in that next line, liver conjugates the bilirubin with glucuronate or sulfate. Conjugation reactions, the liver's good at conjugation reactions. That means adding something on. Well, if it's adding on glucuronate, what's glucuronate? Anybody know? Did we talk about that?
Is it related to hyaluronate as well?
No.
Okay.
Glucuronate kind of reminds me of what? Other than hyaluronic. Glucose. If you were going to make a look at glucose is a six-sided ring where one of the nodes in the ring is an oxygen, and carbon number 6 of glucose sticks upward like this. So this is what I use for glucose, my model, because I never spent the money to get those little tinker toy things for organic. So if this is glucose and this is carbon number 6, CH2OH, we're going to take that CH2OH, carbon number 6 of glucose, going to peel off most of it, and we're going to turn that carbon number 6 into a carboxyl group, COOH, which is a carboxyl group. It's got a pKa that's less than, it's down around 3.4 to 4.4. And so the physiological pH is going to be largely dissociated. So this is no longer glucose because that's a carboxyl group. That's glucuronic acid. It's just glucose turned into an acid. And then because it's dissociated, most of it, we just call it glucuronate, the salt of the acid. So it's got a charged group. It's based off of glucose, which likes water, and the carboxyl group, in the dissociated form in particular, is also going to be hydrophilic. So we're going to add that onto the bilirubin, and we're adding polarity to it. So we're making the bilirubin like water more, making it more water soluble. Okay. Making it easier to keep out of the body once we get it out of the body. Or we could add sulfate, and sulfate, obviously, a large concentration of oxygens, electronegative, they also like to be around water.
So is jaundice an inability of the liver or a problem with the red blood cells?
Is what, jaundice? There are a variety of different possible reasons. It can be liver, it can be, the liver hasn't developed well in a premature infant, and that's usually the case there. So you use the lighting. It can be the rate at that red blood cells are breaking down too fast, or it can even be the rate at which you're trying to get rid of it is too slow. So, rate of red blood cell degradation, rate of synthesis of bilirubin, rate of excretion of bilirubin, primary.
Is it, so it's the biliverdin that makes the gallbladder greenish, right?
Right,
And
the
then,
precursor of bilirubin.
okay, and then when you excrete the bile, is the bile also supposed to be green? Or is it?
It tends to be, yeah, it tends to be greenish yellowish color.
So is there like remnant biliverdin still in the bile?
I would guess, don't know. Okay, let's take a quick break, and when we come back, we'll finish this, and then we'll actually look at carbohydrate contaminants. I'll try and get you.
So is that based just on that information or everything that
When is it?
Wednesday.
So, I think it's up through this stuff.
Up to this legend.
Yeah. Not including whatever comes.
It's not based on like any sort of team information like everything. It's just a big.
Yeah, you're gonna have like,
Everything's good, yeah.
15 questions, 12, 15 questions.
Based on the slides or based on the video?
Based on everything we've done up through that. That would all be fair game. Now, obviously, we can't ask you about everything, because we only have 12 minutes.
Did you say it?
No, I want
Yeah,
you
you
to
go.
keep answering.
Yeah, you get it.
Correct. Okay, look, for team-based learning on Wednesday, it's through living. The question, fair game is anything we've covered in the course through living, which we haven't quite finished yet.
What is
Okay?
it we covered, like you and us, or like other
That
people?
you covered,
Okay.
okay, not just me. Okay? There'll be 12 to 15 questions. You sit down, you take it on ExamSoft. Or no, no, but you take it alone and then you take it with a group. When you take it alone, do we use ExamSoft or do we still use Scantron? I don't know, it'll be one or the other. We'll either give you Scantrons to fill out,
Will we do
I
the
think
alone?
that's what we do.
Will we do the alone and together on the same day?
Yeah,
Is the noodle?
yeah. We'll give you a quiz, you have to take it by yourself. No looking at other people's papers or things like that. So you take it by yourself. You ever done that before? Hopefully. Okay? Then you turn that in. Get your head down.
Question.
Oh, about that?
No.
Well, then why are you
It's
asking?
about this. Do we do it in here? Do we do it in like sim or something?
We do it in whatever lecture hall we're booked for. So you're gonna be sitting cheek to jowl. Okay? So you're gonna sit there, you're gonna take your test or your quiz. And then we collect the quiz, the answer sheets, and we collect the questions, question sheets. Then we will, well, you've got it, it's already posted, who's in your group and where you should go for that date. So Heather has located rooms to spread out. So it'll probably be 4 or 5 groups if it's in this room. 4 or 5 groups that kind of go
Right.
into separate spaces. You take exactly the same quiz, except this time you need to talk to each other. Because this time you have that scratch and sniff. And everybody in the group gets the same score as everyone else in our group. So if you disagree and you're outvoted and the group is wrong, you lose the points too. But it's not as bad as it sounds. One, you can remind them every other question after that. I had that one right. Okay? But if you scratch off and you don't get the star, if it's just blank underneath, you keep scratching off until you get the star. But for every one box that you scratch off that isn't a star, you lose 5 points out of 100. Oh my God,
The
Tim.
group turns in.
But you
one
got
sheet.
5 to 6 people thinking about it, you shouldn't get that many wrong,
Right.
right? Now, who gets to scratch off the scratch and sniff?
Team leader. Just elected, I guess.
Somebody you trust to be scratching on the correct line. Oh, Tim, I made a mistake, I was 1 off. Yeah? Lost 5 points. Because I'm that kind of guy.
So it'd be either your questions, the other questions, and his questions.
Whoever's been lecturing or teaching.
Can you go over how it's graded towards our final grade? Or how
It's about 20% of your final grade.
and how does individual?
And the individual is worth 30% of that 20%. So 0.3 times 20 is 6. 6% of your final grade is how you do on your own. I feel the vapors. Hold on just a second. 40% is how your team did together on that same quiz. Now, usually, teams are scoring close to 100%. 80, if you're a dysfunctional team, you're down around 70 or 80. You gotta find out who to listen to in the future. Okay? So that's why it's worth a lot, so 40%. And then, so that would be 0.4 times 20 is 8% of your final grade. And then there's something called the application question. It may be one or multiple questions. It may be multiple choice, or it may be fill in the blank. That you do as a team. Once again, everybody in the team scores the same amount. And you can use external resources. So only once you get to that application question can you turn on your computers or look at.
So we would turn in the team document and then get the new application.
Well, I choose to trust you, so I just send the teams off with both of them.
Okay.
Just know that you can't use your computers or resources.
How many quizzes, we will have, is it
There's only gonna be one,
one?
yeah. They will be a lot of fun, but there'll only be one.
Isn't it the diseases of the liver and kidneys? That's tomorrow.
I don't know. I'm guessing not. I'm guessing not. There's gonna be gaps. We got the test that we can ask all sorts of questions on. This will be largely from stuff I've talked about.
You said there's only one quiz, is that for the whole,
One TBL.
yeah, but like, coming TBL?
We called it TBL 1.
Okay, for TBL, yeah, okay, but after that, we're gonna have other quizzes as well, that,
Not GI.
not for, okay.
GI, we're getting close. We got 1 week after
Oh,
that.
okay.
So it's like a venture.
While we're on the subject for the finals, there's a spider diagram.
You want a spider diagram?
Yes.
I'll see if I remember. I'll put a spider diagram on it, then if you don't want to do it, you just skip it now. Just take off. I'll figure that out. Generally speaking, spider diagram works in your favor. Other questions about that? Okay. So let's keep talking about the liver. Maybe we'll just wait for next time to do that carbohydrate. Detoxification and excretion of drugs and hormones. So remember how we talked about at the bottom of the previous page, conjugation of bilirubin to help us get rid of the bilirubin to once we get it out of the body to help it stay out of the body. It's a waste product. That's not the only thing the liver does for trying to get rid of things. We can also process drugs that way. And the way that, and also hormones, the liver is involved with too. So the way that the liver can help with things like drugs, hormones, or even toxins, is to make it easier to keep the thing out of the body. And the way to do that is to make it more hydrophilic. So one component of how the liver is going to detoxify and help to secrete is to make things more hydrophilic. Okay? And this would be good for instance, drugs, which you administer a drug to a patient. And this is a foreign compound. Okay? Drugs that we're putting in our body are, generally speaking, not made by our body. Otherwise, they'd be called supplements or something more like that. But a drug, acetylsalicylic acid, aspirin or something like that, we get it into our body in order to do something, to provide a function for us. But we don't want it stuck there forever. Okay, we want it to be used to treat an issue right now, and then we want to be able to get rid of it. Well, how do you get rid of something that your body didn't make? How can you put something into your body and expect the body to get rid of it? And it's like, I've never seen this before. What am I supposed to do with it? Now, this is pretty clever. How can your body get rid of something it's never seen before?
Well, maybe it's like something it's seen before.
Well, actually, for a number of drugs, things like morphine. Morphine is a great painkiller. And what's his name? It's at Johns Hopkins. He really wanted to get the Nobel Prize because he had a great story. He talked about his lab did a lot of work on this. But he said he was sitting around thinking one day, and I'm kind of suspicious when somebody says they sit around and think. It's like, there's probably something else going on. But I was sitting around and thinking one day, and I wondered, why is morphine so good at reducing pain? I mean, morphine is a plant extract. It's probably binding to something, okay? Binding to a receptor that modifies our pain pathway. Why should our bodies, our nervous system, have receptors for a plant extract that never had been in our body before? That's pretty suspicious. So I bet that there's something, a naturally occurring compound in our bodies that bind to a receptor that the morphine happens to bind to now. That there's a naturally occurring compound in our bodies that tend to reduce pain. And so he went on a hunt, he and 100 postdocs. Forgot to mention that in the presentation. And they were hunting for what might be binding to some receptor that helped to reduce a naturally occurring compound that reduced pain. And what did they find? Endorphins and enkephalins and mu receptors. Okay? So, lots of times there may be something that's naturally occurring and that there are receptors for it. But it doesn't have to be like morphine has some part of its structure similar to the endorphin. Can bind to that part of the receptor. Now, how do we get rid of something in our body that we just injected? Our body's never seen it before. This is brilliant. This is why I was never allowed, I think, to design the human body. I wasn't quite around that, but it's our kidneys. The design of our kidneys allow us to get rid of things. Things that our body never produced. Things that we injected into our body, and it can get rid of them. Why? Because the way kidneys work. Who knows how kidneys work?
They have a glomerulus?
They have a glomerulus. What does a glomerulus do?
Filters
It filters. What part of the blood does it filter?
blood.
Yeah, what part of the plasma? Not RBCs.
Just
Glomerulus filter is pretty much anything that's in the plasma smaller than a plasma protein. All the water, all the glucose, all the amino acids, all the small signals. Anything smaller than a plasma protein gets filtered by the kidney in the glomerulus, the first part of the nephron. And then what's the next thing the nephron does? What comes right after, for those of you that physiology, what comes right after the glomerulus?
Send it
proximal
to-
to
Proximal convoluted tubule. What's a proximal convoluted tubule?
what
kind of
is the-
exchange of ions.
Right.
It reabsorbs almost everything that we just filtered. About 70% of the total volume. We filter 125 mils per minute of plasma. And about 80 to 90 mils of it is reabsorbed in the proximal convoluted tubule, including all of the glucose, all of the amino acids. If you could sit, shrink yourself down and look at a nephron and watch it, watch what's going on, and interact with the different parts. You see the glomerulus, and it's filtrate, bulk filtration of filtrate. 125 mils per minute. Picture that's being thrown out of the body. Your bladder gets stretched to 300 mils of urine, that's when you feel the need to pee. So if we did nothing to that filtrate, every 3 minutes you need to pee. Be sort of like if you were pregnant. Okay? So, and you'd be constantly drinking fluid to replace it. So I look at the glomerulus, I see this rush of filtrate, and then I'm sitting here right over next to the proximal convoluted tubule. It's almost like our nephron went, what was I thinking? This is valuable stuff. And so it just starts pulling things back in as quickly as possible. Such a waste of energy, but it's brilliant. Because what can it pull back into your body? What do your renal tubules pull back into your body? What can they pull back in? Anything they recognize. So if we injected a drug, and it's small, it gets filtered, but we don't have the transport molecules for bringing it back into our body. We don't recognize it, and so it leaves in the urine. And that's where most of our waste products, most of our drug metabolites go. So how come the liver's got to get involved? Well, not all drugs are hydrophilic. So what we need to do is somehow make sure that those drugs stay in the filtrate, that they can't simply diffuse through cell membranes. Okay, if they can move past cell membranes, we don't need them to grab them and bring them in. So the liver says, let me make these things more water soluble. I'm going to conjugate them. I'm going to add things like glucuranates, a real common one for conjugating. It's going to make things more hydrophilic, allow them to get trapped in the urine, and leave the body for good. Now another thing happens when we're conjugating, because whatever that drug or hormone might be, what happens is once we conjugate it, its structure is different. And if it's a signal, or if it's supposed to interact with a receptor, by changing its structure, we can inactivate it, change its ability to do what it was supposed to be doing. Okay? So, two primary functions. A, the drug becomes more hydrophilic, which makes it easier to excrete in the urine. And B, most drugs become less active or even inactive when they're metabolized. Okay? There are some exceptions. The liver metabolizing, for instance, diazepam, like Valium, it becomes more active once the liver has interacted with it. Also, levodopa to dopamine, it becomes more active. Steroid hormones, processing steroid hormones and thyroxine, these are hydrophobic signals. By conjugating them, we make them more water soluble and allow us to get rid of them. So how do we metabolize? I've been talking about conjugation, that's only one type. So there are two main types of biotransformation. There are the ones that are called phase 1 reactions, and these make the drug more polar, and therefore more hydrophilic. These are the types of reactions that take place in the smooth endoplasmic reticulum of the liver, and this is where we're seeing things like oxidation reactions. And the key word or phrase to remember is the cytochrome P450 system that we find in the liver, and these are mixed function oxidases. They help to metabolize and make them more water soluble. There are things other than the cytochrome P450 system. There are reductases and hydrolyses, etc. But remember cytochrome P450 in the liver. The phase 2 reactions can either take place on their own or after phase 1 reactions. And this is where we're actually conjugating. So phase 2 reactions are the conjugation reactions where we add things like glucuronate. We can only remember glucuronate, but we can also add things like acetate, glutathione, glycine, sulfate, methyl group. But in particular, remember glucuronate, common conjugation substrate. Yeah.
Can you explain what conjugation is again?
Conjugation is just adding something. And in this case, we're adding something that likes water. So to make it easier to trap it in an aqueous environment, if that happens to be in the plasma and it gets filtered, it's stuck in the urine. I've got one note here. When metabolizing drugs, if you're taking that drug or you're administering it frequently, it tends to enhance or increase the components of the cytochrome P450 system. And that means that over time, your liver gets better or faster at inactivating that drug. Okay, so prolonged administration of a drug causes your liver to get better at inactivating it, which means that that drug becomes less effective. Right? So you need a higher dose in order to produce the same amount. Well, two different drugs we might be talking about here. Maybe that you've been prescribed a drug to treat some malady, and that over time, because this is a long-term administration, the drug dosage has to keep being increased to provide you with the same effects, desired effects. So that's a illicit drug, but what if it's a drug that you're administering to yourself because you like the way it makes you feel? Now, not only do you start to get, for instance, if it's a psychotropic drug, not only do you start to get less effect because of receptor downregulation, but also your liver gets better at metabolizing the drug. And so both of those things are going to mean that you're going to start using more and more, higher and higher doses to achieve the same effect, the desired effect. So whether it's treatment of a disorder or partying, you can see this happening, and part of the effect is due to the cytochrome P450 system. It also means if you're treating an older individual or somebody who has had liver disease or liver problems, their cytochrome P450 system may be compromised. Now, what would be the effect? What would be the problem there, or the issue, if somebody's liver isn't functioning as well as it should?
Drug is juiced, its half-life goes up.
Its half-life would go up, meaning,
Stronger.
yeah, you may be giving a normal dose for a normal, healthy individual, but in this person with a compromised liver function, the dose, the effective dosage is going to be higher in that person. So you would tend to be increased threat of overdosing the patient with what would normally look like a normal dosage. Right? So knowing your patient's liver function can be really important. Okay? Another thing, another impact the liver can have on drug administration is the route of administration of the drug. If it's an oral drug and it's absorbed in the small intestine, then that enters the hepatic portal system and the liver gets first shot at it. So if the liver can inactivate the drug, it means that this is called first pass metabolism. The liver may inactivate a significant portion of the administered dose before it ever has a chance to circulate around the body. Sort of like those bears that are sitting there on the riverbanks in Alaska waiting for the salmon to come up. They find a spot where it kind of narrows down or where the salmon have to jump, and then they just pick them off as they go. Okay, vitamins A, D, and B12. Liver can accumulate some vitamins, not many, but A, D, and B12 being amongst them. Vitamin A having the highest concentrations. It's nice that the liver can store it. Vitamin A you can have enough vitamin A stored in your liver that you can go without vitamin A for 10 months or so, vitamin D for 4 months, vitamin B12 for over a year. Problem with that, with being able to store things, is this also increases the risk of toxicity. You can accumulate too much and it can have toxic effects. And also the liver is involved in vitamin D processing. The active form of vitamin D is calcitriol. And calcitriol's full name is 1,25-hydroxycholecalciferol. It's when your blood plasma calcium levels are low, you start to make PTH, and PTH, parathyroid hormone, will start to catabolize bone and start to dump calcium and phosphate into the blood. And PTH also will stimulate the liver to, stimulates the kidney to form calcitriol to increase absorption of calcium and phosphate from the diet. Now, the role the liver has in that is the liver adds a hydroxyl group to vitamin D to form the precursor of calcitriol. So we'll talk more about that when we do musculoskeletal in the fall. But the liver processes the vitamin D. Iron storage, when you combine ferritin with iron, apoferritin with iron, you get ferritin. And ferritin is a storage form of iron, whereas transferrin is a plasma protein where we transport iron in the blood. So ferritin is found in tissues, transferrin is found in the blood. Both are made by the liver. Somatomedins, or insulin-like growth factors, are made by the liver in response to the presence of human growth hormone. And somatomedin C is the most abundant. That's the other name for that is called insulin-like growth factor 1. And some of the things it does is stimulate chondrocytes and stimulate osteoblasts. So we're going to see it's going to promote bone growth and bone thickness and calcification. And finally, blood cleansing of bacteria. You have blood flowing through intestinal capillaries. That accumulates nutrients, but it also can tend to pick up intestinal bacteria. Okay, and it's kind of scary to me, this one in parentheses. When cultured, intestinal venous blood always shows the growth of bacteria. So we are constantly picking up bacteria from our gut. It's going into the hepatic portal system, but we get rid of them. If we allow them to accumulate, and we can get septicemia, infection of the blood. But we have phagocytic macrophages. These are called Kupffer cells, which line the hepatic venous sinuses and are helping to get rid of and destroy those bacteria that we're picking up so they don't get distributed through the rest of the body. And that's it. And I think not enough. Stop here today and we can do carbohydrate and protein digestion whenever it's on the schedule to do. Sometime I think next week. Okay, and that's the liver. It does everything.